So that part C is the one you need, right? Part C is the one you need.
Yes.
And then let me do a rough sketch on the graph first. So that's 3 minus 3 cosine theta. So it's symmetric with respect to x-axis. It looks like this. See, right? So what I think I will do is I will get the length here and then multiply it by 2. Is it okay? So the perimeter will be 2 times the integral from 0 to pi, okay, square root of 1 plus dr d theta squared d theta. I think this is not the formula. I think it's r squared here. Is it right?
I think so, yes.
And then just plug in numbers. So I need to do a big setup first. Then, yeah, I need to do a big setup first. So r squared is equals to, let me get the 3 squared out, and then I have 1 minus cosine theta squared. And then dr d theta will be 3 sine theta. So dr d theta squared will be 3 squared sine squared theta. So adding them, r squared plus dr d theta squared will be 3 squared parentheses 1 minus 2 cosine theta plus cosine squared theta. That's for r squared. Now then plus sine squared theta. That's for the dr d theta squared. Okay, so this guy here is this. This guy here is this with common factor 3 squared.
Okay.
Okay. Now then inside.
That would be 2 minus 2 cosine squared.
That's right.
I mean cosine theta.
2 minus 2 cosine theta. Let me factor the 2 out also. 2 times 3 squared, 1 minus cosine theta. But some side note that 1 minus cosine 2x over 2, that is sine squared x. Is it right?
Oh yes, minus. Yes, it is.
Right. So this will then be 2 times 1 minus 2 times sine squared half theta. Is it right?
Okay. Yeah, I've seen you do this before in a different problem, which I actually wanted to go over that one too. Because yeah, okay.
This is this basically 1 plus cosine or 1 minus cosine. We can make it into half angle.
Okay.
Why half theta? Because of this. If this is 2x, then this is x, half of that. Right? Okay, so if this is 2x, this is x.
Yeah, that makes sense.
Okay, yeah, actually one of our friend actually asked that. Okay, why it's half theta? So because of that. Okay. maybe we write, if I write it another way, you can see it this way. So 1 minus cosine the x is equal to 2 times sine squared x over 2. Right? You move the 2 here. Okay. And then you substitute the 2x becomes x. If x becomes x, then x becomes half x. Now then this is 2 squared, 3 squared, sine squared theta over 2. Okay, so the square root of that you see the setup is actually a lot longer. Will be 3 times 2 times sine theta over 2. Supposed to be with absolute value, right? But in the domain 0 to pi, in theta between 0 to pi, theta over 2 is in quadrant 1, right? Okay, and sine there is positive. That's why we can ignore the absolute value. Now then, coming back here, this is equal to 2 times integral from 0 to pi, 2 times 3 sine theta over 2 d theta. So
Well,
it's
you're right. The setup is what takes the longest.
yeah, yeah.
From here, it shouldn't be difficult.
That's right. Okay, is the answer 24?
Let me check.
So this is 2 negative 2 cosine theta over 2.
Yes, it's 24.
From 0 to pi. Yeah, that's 24. So the integral itself is easy. The setup is the one takes a lot longer. I unintentionally write them next to each other. So you see, and a lot more thinking, not only longer, but also more thinking. I think the key step is actually with the double angle, like how to absorb these, which is 2 terms, into a single term, and luckily that's a square. I think that's actually the key step.
It's funny because I actually got confused. But I guess it's like along the same lines anyway. Because number 2, part C, that's where I got the most stuck. And then I realized that you had changed it to 2 sine t over 2, and that's the part where I got. That's where I got stuck. Ow.
Oh, I see.
Yeah.
Yeah.
I actually had to highlight it because I was just like, where did he get this from? And then I saw in part B, that's where you had done it. I'm like, oh, that makes sense.
Yeah. Hey, by the way, Dorleans, well, this is recorded. I'm sorry, so I'm not supposed to. Well, something nice. I'm really happy with your test too, by the way. Very happy with your test too. I think you're the high score.
I think there was one that was 85, I think.
Oh, yeah? Not you? Not you are the high score?
I got.
But you're high 79. Enough.
Yeah, I got 79.
Yeah, I somehow think that you get the high score. Matthew is the high score.
Yes.
Hey, but I'm really happy with the result from some of you. Actually, then you can see that you guys improving.
Yeah, because I think
Right?
everybody was like, we can't do as bad as we did last time.
Yeah, once you how to say this, like
I'm actually thinking well, I don't know, maybe I'll talk to you later about this, but I kind of want to see if I should retake the first exam just because I think
there's
I
no
know better
retake.
now.
There's no retake for the first if you took it
No?
already. No,
Oh, I
I'm
thought I could.
sorry.
Okay then.
No, makeup test is not test retake.
The what?
Makeup test is not
Uh-huh.
test retake.
Oh, that's right. Okay.
Yeah, makeup test is if you miss that test, then I can give you a
Oh,
makeup, right? But if
okay.
retake, no.
Mhm. Well, then I have to really try with this one because this one's kind of frustrating me, this section, because I've done all the homework and I even did the even numbers, and I swear to God, I'm like, I don't know what I'm doing.
That's learning curve. You still have couple days, right?
Yeah, I know. But it's frustrating because it's like I've been, I actually had it more with time, and like I finished the homework last week, and I just been going over it, reviewing it, and I'm looking at this at the test that these samples, and I'm just like, Lord have mercy.
Give me a second. Which test did I give you guys, by the way? I'm asking this
Fall.
because I want to give more. I think I only
Okay.
gave 2 last time.
Yeah, you only gave 2. It's fall 20. Yeah, fall 20 and
spring 20.
I believe spring 20. Yes, spring 20.
Okay.
There was another one that you had. Let me see. That I also got, but this one seems like there was different. It's from ELAC, I believe.
Oh, that's from my website. Okay. If you
Yeah,
have
from your
question from
website.
there, yeah. If you have
Fall
question from
19.
there,
Yeah, fall 19. Actually, it doesn't say ELAC, but usually it does. But this one is just fall 19.
no, fall 19 is at West.
Oh, okay. Yeah. So fall
Fall
19.
T19.
Mm-hmm.
Which question?
Let me see.
You know what? Let me post it also. Okay. So
Okay.
let me
Okay.
post it also there. I will post it on April the 26th discussion board.
Okay.
That was fall 19. The reason you happen to have a hand on it, which is good, but especially because you have a hand on it, then I should make it available to the rest of the class also.
Mm-hmm. Well, I went searching through all your stuff last week, so I was.
It should be. I think fall 19. I still have it on my website.
You do, because that's where I got it.
Yeah, but some students, I'm so surprised with my statistic class. I have some students actually say, Thomas, where should I get your old test again? I was like, what?
Oh my God. I mean, at this point, it's like we're past the half point.
Yeah, it's just like, where have you been?
Oh
I'm
God.
uploading it. Give me a second.
No worries.
Okay, I post fall 19. I think those 3 are representative enough. Let me see. Which question?
Hold up. Let's continue with fall 20. I was gonna
fall 20.
ask. Yeah. Let's see something. You know what? No, actually, no. That's fine. I can deal with that later. Where is it?
Oh, some warning for
Yeah.
the rest of the class. I have seen somebody did this. I have seen somebody did this as square root of 4x squared plus 1 equals to 2x plus 1. That is not true. That is so not true. And whoever did this, honestly, I was not mad when I saw that. I was laughing out loud. It's like, you must be so anxious that you don't realize this is wrong. Now, the thing is, 2 people did this in the last test, okay? And 2 of them also didn't do that in the next question with the same setup. So I think, I forgot which question was that, but let's say in number X, that person did this mistake. Okay, and then in the next question, that person didn't do this mistake simply because we have 2x in front of it. You know, please don't repeat this anymore. Okay, please don't repeat this anymore. Okay, a very, very easy counterexample is the application of Pythagorean theorem. I mean, I don't even need to show you why this is wrong theoretically, but if you apply this, right, we know 3 squared plus 4 squared equals to 5 squared. Right? But if these were true, then this will be 3 plus 4. But no, that's not 5. You see? Okay, whoever did this, I think I owe you. No, not I owe you. Your Algebra 1 teacher owe you an explanation. Okay, I'm the one paying for that person. What kind of Algebra 1 teacher is that? Or maybe you just get too anxious that whatever you learned before being thrown out of the window. Okay. Now let's see. Okay, going back to you, Darlene.
Oh yes. Can you go over number 5, B and C?
Number 5.
From
B,
fall 20.
Fall 20, number 5. B and C. Okay, so a to the n over n factorial. So now this is fall 20, math 262, test 3, number 5b. So a sub n is n to the n over n factorial. The sequence, right?
That's number C.
Oh, that's numbers. Oh, so but you want me to go for C also?
Yeah.
Okay, let me go for that one first then. Now, the way I do it is this. So you see the first term is easy. That's a 1 over 1. The second term will be 2 times 2 over 2 times 1. The third term, so what we do here is actually look at patterns. Okay, so the nth term will be n times n times n times n all the way n times over n times n minus 1 times n minus 2 times n minus 3 all the way to 1. Now, notice that this is greater than, now you pair it this way. This is 1, right? This is 1. Now, how about n divided by something less than that, but positive? Then that
less than 1?
No, greater than 1.
Oh.
Right? See, you can see that here. You can see that here. You can see that here. Maybe I color that blue. Is it right? So this one is equal to this one is equal to 1. Okay. But every term after that will be greater than 1. Okay. Every term after that will be greater than 1. So this is greater than 1. Actually, this is greater than 1. This is greater than 1. So all the part that is greater than 1 are here. You compare that to 1, right? Now, the last term, however, that's equals to n. Do you see that?
Yeah.
Okay. Now then, what happened here? Then a sub n is greater equals to n, but n goes to infinity, right? So a sub n actually not only divergence, it's divergence to infinity. Okay, by comparison. Not comparison theorem, is by simply definition of limit. It's bounded below by something infinity, so that guy must be infinity. So instead of we attacking it as a whole, we attack that pair by pair.
Okay.
Is the notation with arrows okay for us to use on the test? Yes, it is okay. It is okay.
So basically what we're saying is an is greater than 1 or greater or equal to 1, but as it approaches to n, and because n approaches to
Oh, no, 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 no,
infinity.
no, 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 no. So take a look here. Take a look here. Maybe I insert something in between then. Maybe I insert something in between.
Okay.
Now, notice that then in between, this is equal to n over n, n over n minus 1, n over n minus 2, n over n minus 3, all the way to n over 1. Is it right? Okay, now, but if you take a look on each fraction, this is equal to 1.
Yes.
And this is greater than 1. Also greater than 1. Also greater than 1. This guy also actually greater than 1, but we can be more precise. This is greater than, this is equal to n.
Okay.
Okay, so if I multiply this, I can compare this to 1. I can compare this to, this is the one, this is equal to 1. This is equal.
So basically from like those two lines that you're working on right now, that's where we're doing our comparison.
Yes, but you compare that factor by factor.
Okay.
Yeah, you compare them factor by factor. Okay, now if you want to make it even stronger, you can say that the term right before that is n over 2, right? So n over 2, so you can keep this here, n over 2, and then n. For the last two terms, the last two factors instead of only the last factor, such that this is actually n squared over 2. You see? Okay. So it depends on how many factors you want to take. You can make it n times n over 2 times n over 3 also, which means this an goes to infinity a lot faster.
Okay.
Right? But well, the consideration here is where it goes to. It doesn't matter how fast it goes to that place. So using n is good enough, but what you can do, you can also do it this way.
Yeah, I think that this is where I've had my issue. Like I understand it to some degree, and then once I see it like spread apart like this, I was so confused. But okay, now I'm understanding it better.
Start with this. I think if you see the a sub n right away, of course, that's the solution. I think when I write the solution, that's how I write it, right? But start with the first couple terms just to have feeling on that. Even though you need to be also careful, because there have been cases where the first couple terms, it seems to be bounded, right? Like in this case, it's bounded below by 9 over 2. But when you go further and further, then it's actually becomes decreasing. The bound actually decreasing, go down to 0. I have seen that case, but I mean, I mean, the purpose you write the first couple factors out so that you can get the feeling on how the terms actually behaving, at least in the first couple terms, in the first couple, the first couple terms. Okay, and then everything after that is really just arrangement. Okay, let me see part B. Where is that? N tangent 1 over n. That one is. So 5b is the nth term is n times tangent 1 over n, which I can rewrite as tangent 1 over n over 1 over n. Is it right?
Could you change 1 over n to a different variable?
Yes and no. You can change to another variable, but you need to define that as a new function, the superposition function.
Right.
So you say let f x equals to x tangent 1 over x, like that. Okay, and then note that fn equals to n tangent 1 over n, which is a sub n. And fx is continuous on 1 to infinity, right? It is discontinuous at 0. It's discontinuous. Maybe I write it this way then. It's continuous everywhere. Yeah, I should not say it's continuous. It's actually discontinuous at other places also. But for sure, once it is 1 to infinity, then it is not. Then the reason I need that is because then when I do the limit, x goes to infinity of x tangent 1 over x, this is equals, this is the time writing it as a limit is important, okay? Instead of just writing the expression without the limit. The reason is I will play around with the 1 over x. You said that you want to substitute that, right?
Yeah.
Okay, so if x goes to infinity, then 1 over x goes to 0 positive. To be more precise, 0 positive.
Okay.
Okay, so let me make it like this. This is limit 1 over x goes to 0 positive. How about that? Now then replace that 1 over x by a dummy variable, let's say t. Okay, but what is this equal to? That's 1. Okay, so by continuous superposition function, a sub n converges to 1. Maybe to be more precise, a sub n, which is n tangent 1 over n converges to 1. So you, when you say substitution, it seems like you already see that this is tangent x or tangent blah over blah. When blah goes to 0, it goes to 1. you know. But the thing is, we need to have some interplay between the 1 over n, which is discrete, and when n, which is discrete, so 1 over n also discrete. There's a lack of continuity there, right? Okay, so it will be better if you attack that from the continuous superposition function.
Right. Yeah, that's what I meant. To change the variable bit through using the superposition function. Okay. Can we go over number 6?
Number 6, let's see. Oh, this one. That's e to the b. The answer is it right? Yeah, the answer is e to the b.
Oh yeah, it is. That's the answer.
Give me a second. Let me quote unquote that. That happens to be a very some kind of like sequence that I ask a lot. At least I went over that a lot in some of my classes. Maybe not with you because I thought it's already in the lecture. Two ways to approach this. Let's see the silly one.
Okay.
So a sub n equals to 1 plus b to over n to the n. Now, you see it this way. This is 1 plus b over n to the n over b times b on the exponent, which is
Wait, why?
because of this. You see that 1 plus 1 over x to the x. If x goes to infinity, this is equals to e. That's one of the definition, by the way. Okay, so we know that 1 plus 1 over n to the n by continuous superposition function, this is also equals to e. Right, this is just what I write on the right hand side is background. So my plan is I will change this n here into n over b. So I make it into n over b here, which is the same expression with n over b here to the power of b. Now this guy, so if n goes to infinity, then n over b goes to infinity also, right? For positive b, of course. Is it right? Okay, but then that's exactly what happened here. That's e. This guy here is e. Now that's something I don't expect any student to see. So let's do it the long way. Okay. So a sub n equals to 1 plus b over n to the n. Now I will construct a superposition function. Let fx equals to 1 plus b over x to the x. Let's call that y instead of fx. Yeah, fx first, because I need to say that this is a continuous superposition function. Note that fn is 1 over b, 1 plus b over n to the n, which is a sub n, and fx is continuous on 1 to infinity. In fact, it's continuous everywhere except 0. Now then, call that y equals to that and apply natural log. Okay, now then apply limit. Limit x goes to infinity of natural log of y equals to limit x goes to infinity of x ln 1 plus b over x, which is equals to, on the left hand side, it becomes natural log of limit. On the right hand side, I will rewrite that into natural log over 1 over x. Now, because the purpose is I will use L'Hopital rule. So that will be 1 over 1 plus b over x times the derivative of b over x is negative b over x squared. At the bottom, however, we will get negative 1 over x squared. So we get limit x goes to infinity of, notice that everything cancels here except the b, right? Except the b. So I will get b over 1 plus b over x. But when x goes to infinity, it will be b over 1 plus 0, which is b. So limit x goes to infinity for y is, you see that we have natural log here, right?
Mm.
Then it becomes e to the b. Now then from here you go on by continuous superposition function, then the sequence is convergent to e to the b. Now, one of you asked me this question earlier. Thomas, can we use that arrow? Yes, you can use that arrow if the n goes to infinity, okay? But what usually happen that I saw a lot is people use equal sign instead, which is not right, okay? Yeah. This notation means converging to, okay? Yeah. So equal sign means that this actually equals to in whatever situation. Now, this notation means implies this is convergent. So these three notation are not the same notation. Okay. Other question?
I just realized that fall 20 and spring 20 are the same problems.
Oh yeah. So I was
Yeah.
lazy. I was lazy, I believe, at that time.
I know. I mean, like they're literally the same problems.
Okay, so I basically just give you the same questions. I
It's
don't
the
know.
same, yeah, the same numbers too. Like everything is the same. I'm looking at. I have the fall 20 on my tablet, and I'm looking at the spring 20 on the computer, and I'm like, this is the same thing. Because I only worked on one. So and I was looking at the other one, the one I mentioned to you earlier. Can you go over? Give me a second. Oh my god. Number 4, part B.
Number 4, part B on fall.
Well, fall 20, spring 20.
Fall 20.
Yeah, they're both the same thing.
So number 4, part
yeah.
B.
Yeah.
Okay, let me screenshot that first so that I don't need to copy that anymore. Number 4, part B. And what is part B? We'll find the area outside of C to inside C2, outside C1. Okay, I believe part A is the sketch. So let me sketch it first. I have to sketch this one. At least get the feeling on what it looks like. So C1 is a circle centered at -1.5, comma 0. So that's the circle. And then C2 is, so it looks like this. No, it's way too big. It's only 1. So it looks like this. So we want the one inside the heart, but outside the heart, but outside the circle. Oh, so it is inside the heart, outside the circle is this one. Right? That's inside the heart, outside the circle. So later on, our integral will be let me solve it first. So r equals to -3 cosine theta equals to 1 minus cosine theta. Like I need to find where the theta intersect. And then that's -2 cosine theta equals to 1 cosine theta equals to -1/2. So theta in quadrant 2 will be 2 pi over 3. And in quadrant 3 is 4 pi over 3. Okay, and we can see that they also intersect at r equals 0. Now I will just do the one here. I will just do the one here. Okay, the top one. I will just do the top one. So the area equals to 2 times the integral of, oh, there's a 1/2, 2 times 1/2 integral from 0 to 2 pi over 3. The outside functions are squared. That will be, so the inside, the red one, that will be 1 minus cosine theta squared. Hold on. The thing is, how to explain this better? So we will deal with the top. Okay, we will deal with the top, but the devil is in the detail apparently. I want to zoom this. Oops. I want to zoom this. Let me zoom it. Now, here's what happened. In the first quadrant, it's simply the heart. Right? In the first quadrant, you only have heart. Is it right? Okay. Now, in the second quadrant, however, if you zoom it even further, it looks like this. It looks like this. So this is part of the heart. Okay. Now, and then part of the circle looks like this. Okay. So in quadrant 2, if you shoot in certain angle, in that angle, you need to subtract the red one squared minus the blue one squared. You see what I mean? Not like in quadrant one, it's only red one. In quadrant one, you have only red one. You see? So what happened is then I need to break the integral, basically. I need to break the integral into two parts. The first one, the one in quadrant one, from 0 to pi over 2, only the red one, which is only the red one, the 1 minus cosine theta squared d theta, plus then in quadrant 2 from pi to 2 pi, from pi over 2 to 2 pi over 3. But then I need to subtract 1 minus cosine theta squared minus, what's that? Negative 3 cosine theta squared d theta. That's the setup. Okay, that's the setup.
Okay, wait a minute. So the green part is the first part, the integral from 0 to pi over 2, which is 1 minus cosine theta squared.
That's right.
Okay, because this. Oh, okay. Oh, because the circle is negative 3 cosine theta. Okay, hold up. Plus, and it's 2 pi 3 over. Wait, why is it going backwards?
Huh?
Why is the oh, hold up. I think I'm getting it, but I'm also thinking I'm confusing myself.
Okay, take your time. Take your time.
The integral 2 pi over 3 to pi over 2. Why is it that way? Why is it going backwards?
Well, I start from the bottom, from pi over 2 to 2 pi over 3.
All right, A to B. My bad. Okay. Oh, another question. Where did you get the half from?
Oh, the formula for area. That's half integral function squared.
Oh, because the 2 is technically from, because you're trying to get
and
both.
The bottom. Yeah, the
yes,
top and the bottom.
Okay. Oh, okay. Got it. Okay.
Okay, now let me screenshot what the details look like, and give me a second. Let me screenshot that first and bring it to your attention. So what happened is this. Let me see, I have a chat coming in. Shouldn't the first integral go to 2 pi over 3? No. The reason is because if you see here, right? The first part of the integral from 0 to 2 pi, I have the heart only in full. Only this part. You see there's no red, there's no circle in there. Okay, yet once I get into the second quadrant, then every time I shoot in theta direction, notice that it will intersect the red one, right? Intersect the red one. Okay, so in the first quadrant, we totally have only the second curve. But in the second quadrant, the answer is no. It's bounded below by the red one. You see that? It's bounded below by the red one. Oh, did I say that? From 0 to pi over 3? Robert brought up the issue that in my solution, I say it's from 0 to pi over 3.
Oh yeah, you did put that in your solutions.
Then that's a mistake then. That's a mistake. That's a very big mistake. That's a very big mistake. So that's, it should be this one. The setup should be something look like this. Should be like this. Yeah, the setup should be like this. Which, if you think about it, that's basically the integral from 0 to pi over 0 to 2 pi over 3 for the cardioid minus integral from pi over 2 to 2 pi over 3 for the circle. Yeah, so that's what it should look like. Yeah, that's what it should look like. Let me see my solution. Oh, no, not that one. Give me a second. Wow, that's a very bad technical mistake though. That's from 420, you say? Let me see that again. Hold on. That's what I did though. Oh, I see. Okay. This is what I did in my test, the second line. But you see, that's because this is exactly the same function with this, right? So I can combine them into this guy, right? The domain of integration, and then subtract it by this part here, which is only for pi over 2 to 2 pi over 3. You see? Okay, so I think what I did in my solution is correct. Yeah, what I did in my solution is correct. Basically, the idea is I will get, if we see here, I will get, let me erase something first. So I will get the total area from here all the way to here. Okay, but that's a line here. Let me erase this line also. Okay, so I will get the area the total area here. And then I cut the crescent away. You see that? Right? Yeah, that's what I did in the test. Now, the thing is, the common mistake was that people think that this is from 0 and this is to pi over 2 or 60 degrees, but no, it's not. Okay, when you have -3 cosine theta, when theta equals to 0, it starts from here. Okay, that's when theta equals to 0 up to pi over 2. This is when theta equals to 0. This is when theta equals to pi over 2. And this, when it gets to theta equals to 2 pi over 3. Okay, so the green one is actually from pi over 2 to 2 pi over 3 of that circle. Okay. So what I did in my solution is already correct. No, I was so afraid that I make a wrong solution. But it was correct. It was correct. Okay. Now can you go on with that integral stuff? I think somewhere in between you need to use double angle formula.
Yeah, it's fine. Like it's like, but like you said, it's just the setup that's difficult, because I would have not done that.
It's the setup. It's the setup.
Okay. Yeah, because now that you kind of explained it that way with the graph, explaining where -3 cosine theta is at 0, or at -3, I mean, it kind of makes a little bit more sense.
And I believe I believe I took this question from somewhere. It's not my own question, but then the reason I chose this question is because of that part. Because of that part, you need to be aware where is your where's your position at what theta, and also realize that the period for this circle, the blue, the red one, the period for this circle is actually only pi, not 2 pi. It forms one circle. It forms one circle from 0 to pi. Yeah, it forms one circle from 0 to pi. So if I put it here, this is when theta equals to 0. This is when theta equals to pi over 2, and it goes back to pi. But you can only see that if you ever graph it on your own. You know, I can use my graphing software to show it to you. Give me a second. Let me use my graphing software to show that to you. Of course, what you see here is just a circle, right? What you see here is just the circle. Now, how do we know that it is actually from 0 to pi instead of 0 to 2 pi? Now, you see the theta here is from 0 to 2 pi. Okay, now I will change it to from 0 to 3.14159, which is basically the approximation for pi. Notice that I still have one circle. Now, if I make it, let's say from 0 to 1, 0 to 1.57, that's half of a pi, right? And it's like that. Okay. So even though the graph doesn't tell us the direction, by playing with the parameter, you can see the part of that. It's like, okay, this is in quadrant. If my theta is in quadrant 1, this is what it looks like. If my theta in quadrant 1, then the graph will be in quadrant 3. Okay. Okay. Now the fact that the r is actually shooting backward is actually in the equation, but we don't really realize that because we focus so much. Most of the time, we focus so much on the graph only, but not how the graph actually comes up. You know. Okay. And I believe that's the reason I chose this question at that time. It's your trigonometry teacher's fault.
Oh, Thomas.
Who's that?
I don't know. Some guy at West. You so mean.
And everybody failed the class.
Oh, like 3 of us passed the class.
I think at that time there's another one guy.
Yeah, I think there was like 2 guys, and it was
2
me and
guys.
Brittany.
Yeah, so not 3. Who taught you arithmetic?
The what?
Who taught you arithmetic? That's not me, definitely. You
Oh,
say
no,
3
no, no.
passing, but now you say 2 guys, 2 girls. So all guys only half human.
No, I said I think there were 2 guys. I'm not sure.
I'm not sure there are only 4. As I remember, there were 6 people at the time. As I remember.
Well, for the final, you mean? Because the final, there was a few more people, but that was also because
No,
they
the
were
one
put
passing.
together.
Yeah, the
Oh,
one
okay.
passing. As I remember, there were 6 people.
Well, because I only saw 3 or 4 of us in the class or during lectures. That's why. So that's why I said 2 or 3. But I know, like, me and Brittany, we were always there. So
There's actually one guy. The other one guy there is actually doing very, very well too.
Are you still taking math classes?
I bump into him, I think, the next semester, and I think he was doing very well in his pre-calculus too. You know his comment all time is that pre-calculus is actually a breeze compared to your trigonometry. I say, well, I don't really hear the otherwise yet. Oh, it's well anyway. Other question. Let me see. Robert, do you have any question? Bring it up. By the way, Robert, just make sure that you throw in your question, because otherwise Dorlin will ask all the question and give you no chance.
Yeah, no chance. Can you look up the one from fall 19?
Fall 19.
Yeah.
Sure. Let me see. Fall 19. Yeah, because Robert's microphone is not on, so Dorleen's not aware that he's here. Okay, which question, Dorleen?
Okay. Can you go over number 6?
Number 6. I hope that's easy.
Maybe for you.
Oh, this one. Okay. Number 6. I know I picked this question from somewhere. That's so not my wording. Yeah, consider this sequence. Find the formula for general term a sub n, start from n equals to 1. So let's see. First, the one I noticed right away, it's alternating.
Yeah.
Right? So let's take care of the alternating first. A sub n, start from 1, -1 to the n. Because when n equals to 1 is negative. Okay, now on the numerator, start from 5, I keep on adding 6. So on the top, that's linear. Right? On the top, that's linear. So that will be, so imagine linear function instead of linear sequence, which is supposed to be called arithmetic sequence. But it's linear functions. The slope is n. Right? So it must be 6x plus or minus something. Okay? 6x plus minus something. And then when n equals to 1, you start from 5. So I subtract by 1. Is it okay so far?
Yeah.
Now the denominator, this is 2 squared, 3 squared, 4 squared, 5 squared. So that's, but it starts from 2 instead of from 3. So it will be n plus 1 squared.
Oh.
Okay, so this is the blue, this is the yellow, and let's say this is the This is the green. Okay, now determine whether the sequence converges or diverges. If this converges, find the limit. I notice that this one here on the top is degree of 1, the bottom degree of 2. So it will converge into 0. But with the plus minus, I will do this then. Absolute of a sub n. That's how I get rid of the plus minus, right? Dealing with only the positive terms. That's equals to 6n minus 1 over n plus 1 square. Now then I will divide by n. So 6 minus 1 over n over, no, divide by n squared. Let's divide by n squared. So that's 6 over n minus 1 over n squared, big over n squared over n squared plus 2n over n squared plus 1 over n squared. That is equals to this. But this is convergent to 0 minus 0 over 1 plus 0 plus 0. That is 0. Okay. Now, since absolute of a sub n converge into 0, then a sub n, which is negative 1 to the n times 6n minus 1 over n plus 1 squared, is convergent to 0.
What happened to obviously I see the absolute of parentheses -1 to the n power. What happened to the n power?
Huh?
What happened to the
negative 1 to the n? It's either plus or minus.
Oh, so it's nothing. So the n power
it's either plus or minus of that, even though this notation is incorrect. Yeah, but negative 1 to odd number will be negative. Negative 1 to even number will be positive, right? But
okay,
once you put it in absolute value, then it becomes just positive.
Okay. So nothing happens. So the n power just goes away with the absolute.
Yeah, negative 1 to the n just being canceled by the absolute.
Got it. Okay.
So pictorially, it looks like this. So let's say when n equals to 1 is here, n equals to 2 is here, n equals to 3 is here, and so on and so forth. It oscillates around the x-axis. Okay, now, but once I apply the absolute value, this guy becomes here. This guy becomes here. This guy becomes here. This guy becomes here.
Okay.
You see? And it converges to 0. So if the absolute value of the sequence converges to 0, then the sequence converges to 0. But it only if the absolute value of the sequence converges to 0. If it converges to other number, then it's not. Because
right.
Yeah. Okay. So it may be that we may have, well, just go with plus minus 1, right? Plus minus 1. Yeah, plus minus 1. The absolute, maybe I write it formally. Note absolute of a sub n converges to something else, it does not imply that a sub n converges to that. Okay, counterexample. So the example to counter the conclusion that we want to show that it is not true, right? So we use the a sub n equals to -1 to the n. We know that this is divergent. That's -1 when n is odd. It's 1 when n is even. Yet, absolute of a sub n is equals to 1 all the time. So the absolute value, if the absolute value of the sequence converges to something other than 0, then the alternating sequence is divergent. To be more precise, it will be divergent to those two non-zero numbers. Okay. So I think the hard part here is more into part A, how to set it up. There are 3 parts there. Now for part B, I can just tell you that you use this theorem here. If the absolute value of the sequence converges to 0, then the sequence itself converges to 0. Okay. Now that gives us something else. Now suppose I was once thinking to ask this question sometime in the past, but I canceled it, you know. But let me use that. Suppose we have this sequence, -1 to the n times, let's say, n over 2 to the n. Now notice that, let's say this is our sequence, okay? Now, notice that this is convergent to 0. Okay, why? This is convergent to 0, and the proof is the absolute value of the sequence is n over 2 to the n. Right? And this is n over 2 times 2 times 2 times 2 n times. Basically, eventually you will see that this is actually convergent to 0. Okay, one of them linear, the other one exponential. When you look at the continuous superposition function, you will see that's convergent to 0. Okay, now, however, I have seen a question like this only at a very high level though. No, I mean very high level, like when I talk about MIT or Harvard. Some teachers actually ask this question. That person actually put cosine of -1 to the n over 2 to the n. What will that convergent to?
Well, if the proof is that the absolute of, well, n over 2n converges to 0, wouldn't it be 1?
Yeah, then this will converge into cosine 0, right?
Yeah.
Which is 1. Okay, now then the next step, that teacher, that professor actually put something else. Let's say put 3 to that. Not to the cosine, but to the first term. Now, the mistake that was made by that he expected here is somebody put absolute value for the whole Cn. But we're supposed to put absolute value only on that alternating terms, only on this one. This is already constant, right? So this is actually convergent to 3 plus 0.
Mm.
Now, the way he wrote the question, not exactly the same question, the way he wrote the question actually is he tried to confuse students also, I think. He wrote it this way. Let me see. He wrote it with, so -1, -1/2. So he wrote it as -1/2 to the n, -1/2 to the n times n. So he tried to hide the fact that it is actually alternating and combine the exponential at the bottom together with the alternating part. You know.
I mean, but even if it changes from -1 to -1/2, wouldn't it still be alternating?
Yes, it is still alternating. But you know, some students, they only see it to be alternating if they see -1 to the n. Right? Okay. Well, what makes it alternating here is negative to the n. Now, the 1/2 has something to do with the amplitude. Goes up and down.
Like,
right now, the
like
amplitude
how much up and how much down it goes, right?
Yeah. So the amplitude gets smaller and smaller as n goes to infinity. Okay. Now the thing is, this guy 1/2 to the n converges to 0, yet n goes to infinity. So you will see that this, when you try to do this to show the convergence, you're supposed to use continuous superposition function. And then after that, you need to do L'Hopital rule somewhere in between. I mean, we know that linear functions grow slower. It grows to infinity, but it grows slower compared to exponential function. So he hit the exponential on the denominator by combining it together with the alternator. So once he combines it with the alternator, basically this guy here, okay, it becomes less feasible.
Yeah, that's true. I can see that.
Okay, other question?
Yeah, can you do number 7? Part. Oh, I think. Oh, part A, and then I think number C, or I mean letter C, is kind of similar to what you were just talking about.
Yeah, that's the one. Yeah, but that's so. Is that convergent or divergent for part C?
It says divergent.
Yeah, but do you know
Oh,
why?
it diverges.
Yeah, but do you know why?
No, I don't actually. That's a good question. I don't.
Okay. You break it up with the -1 to the n first. So for that number 6c, a sub n equals to 3 plus -1 to the n. That is equal to 3 minus 1 for n equals to odd. That's 3 plus 1 for n is even, right? So that's 2 or 4, depends on your terms. So a sub n is divergent.
Wait, why is it divergent?
Because it doesn't go to a certain number. It's either 2 or 4.
Oh, I see. Okay.
No. It's alternating. Actually, it's alternating 2, 4, 2, 4, 2, 4 like that. If you write down this sequence, it will be 2, 4, 2, 4, 2, 4. Did you ask me
Wow.
for part A?
Yes, part A.
Part A, so that is the nth term is natural log of n over square root of n. Every time I deal with natural log, I guess I need to use continuous superposition function because I want to use L'Hopital rule. Okay, so solution, let fx equals to natural log of x over square root of x. Fx is continuous on 0 to infinity. Therefore, fx is continuous on 1 to infinity. Note that this fx is the continuous superposition function of the sequence. Okay, now then, limit of x goes to infinity of ln x over square root of x is equals to, I will apply L'Hopital rule. So that's 1 over x at the bottom, at the top. At the bottom, that will be 1 over 2 square root of x. So that will be 2 square root of x over x, but that's basically 2 over square root of x, which goes to 0. So by continuous superposition function, a sub n, which is natural log of n over square root of n, goes to 0.
Okay. Can you go over number 8?
I can.
Is the last one, I promise.
No, that's okay. That's okay. Number 8?
Yes.
So earlier it's number 7. I wrote number 6.
Yes. These last two that you worked on, C and A, was from number 7.
That's for number 7. That's fall. Is it fall or spring 19? Fall 19, I believe.
Fall 19.
So number 8. The first 3 terms. So a sub 1. You know what? Let me copy all the question. Screenshot all the questions and put it there. The first 3 terms. So a sub 1 is square root of 2. A sub 2 will be square root of 2 plus square root of 2. A sub 3 is square root of 2 plus a sub 2, which is square root of 2 plus square root of 2. Now, given that a sub n is increasing and bounded above, state the name of theorem that guarantees the sequence is convergence. That's monotonic sequence theorem. I think in my lecture or one of my discussion, I said monotonic bounded theorem. Monotone. Now then find the limit. So let's call the limit to be A. Let's call the limit to be A. Now then, if the limit is A, then the limit of the n plus first term is also A. Is it right? It's convergent.
Why? What do you mean? What do you mean?
If I go one term further than A infinity,
would A be considered a constant, or is it just
the A, this A here,
yeah.
that's a constant. That's the limit. There's one theorem somewhere. I mean, I think I didn't go over that in the discussion, but it says the following: if the limit of the sequence is A, then the limit of another sequence that comes after that sequence is also A. In this sense, how to say that? So let's see this one. Limit, and this is just an example. Limit of n goes to infinity of all 1 over n. This is equals to 0, right?
Right.
Okay, now how about limit of n to infinity of 1 over n plus 1?
That would also go to 0.
That also goes to 0. Now, there are two ways to look at
Okay.
this. First, you see that as a function 1 over x, right? Compared to 1 over x plus 1. But you can also think that this term, actually, this term of that sequence is actually the next term after that.
Okay. So an plus 1 is just an plus the next one, basically, plus
yes,
1.
the next term of that a sub n.
Oh, okay.
Okay.
Yeah, I had seen it before, but I was kind of confused by it. But now that you broke it down like this, it makes sense.
Now, I will prove that later on. I think I will prove that at least to see the technicality. We are okay, not only by instinct. But suppose, I mean, knowing that this is true, which I will prove later on, then a sub n plus 1 equals to square root of 2 plus a sub n means I can apply the limit to both. So limit n goes to infinity of a sub n plus 1 equals to square root of 2 plus limit x goes to infinity of a sub n. But according to what we know, the limit is a. Both of them a. So a equals to 2 or a equals to -1. But since a sub n is always positive, a equals to 2 only. In other words, limit n goes to infinity of a sub n is 2.
Okay, that makes sense. It's really not that difficult. It's just
No. It actually starts from this basic idea. It's actually one of the question in our book, I believe. But let's.
I have seen it. I think it was like number 60, number 70,
yeah, it's
something like that.
Yeah, some question very far in the section. So let's prove that one. let's say if A sub n converges to n, to A, that implies A sub n plus 1 also converges to A. Okay, now I will prove by contradiction. So let A sub n converges to A, and at the same time, A sub n plus 1 converges to B, which is not A. Okay, basically I'm saying limit and suppose. In other words, limit n sub n goes to infinity or A sub n equals to A, but limit n goes to infinity of A sub n plus 1 is B, which is not A. Okay, now then what end up happening is limit n goes to infinity of A sub n plus 1 minus A sub n is B minus A, which is not 0. Which is not 0. Now it will lead to contradiction. Let's call that C right now. That's the difference. Okay. Let's call that C. You set that to be equals to C, which means limit n goes to infinity of A sub n plus 1 is equals to limit. I want to show that there's a what is that? This is what it means. But the contradiction has something to do with. I'm sorry, my computer seems to be screaming right now. So I mean, it reacts really slowly. See? No, that's not what I meant. But we want to show that it means it contradicts with the original statement that the limit is actually A. Because when the limit is A, by definition, we say that limit n goes to infinity of A sub n equals to A. It means there is a capital N such that for every, no, sorry, a wrong order. For every epsilon positive, there is a capital N such that the difference between A sub n and A is less than epsilon when n is greater or equals to that capital N. That's the definition. Now the thing is, if we have this, which is not right, we start from the assumption to contradiction, right? Now suppose that we have such n, okay, limit n goes to infinity of a sub n plus 1 is equals to b, okay, then the distance between n plus 1 and b is less than epsilon whenever, call that n2 here. But at the same time, a sub n plus 1 is the term coming after a sub n. How to say that? If a sub n minus a is less than epsilon when n is greater or equals to 1, maybe sorry. I try to get the conclusion as fast as I can, but I guess I need to be more patient. So this is the definition of limit, the sequence, if the sequence is convergent, right? Okay, now then, but if the a sub n, the term is already less than epsilon from the limit a, then consequently, a sub n plus 1 from a must also be less than epsilon. Right? Because let's say the n is the 100 term. Let's say this is 100. Okay, this is 100. Let's say this is 100 for sake of being discrete. So any n greater than 100, let's say the 101st term, 102nd term, 103rd term, must satisfy this requirement, right? Okay. Now, if the 101st term satisfy, then 102nd term also satisfy. Okay. So what end up happening is, fast forward. So later on, we will come up with this fact that a sub n plus 1 minus a is less than every epsilon, whatever epsilon you choose, whatever positive number. And at the same time, a sub n plus 1 minus b is also less than any epsilon you choose. Okay, but when you put this together, you will see that a is actually equals to b. A, how to say that? A plus b later on will be less than a minus b, less than 2 epsilon. More or less, I'm not sure the details. But if you have this situation, that implies a minus b equals to 0. You know what? Let me go over again. I will delete all the things I said earlier. I will organize my thought because Be patient with me. Proof. So I will say let limit n goes to infinity of a sub n is equals to a, and limit n goes to infinity of a sub n plus 1 is b. I will show that a equals to b. Okay, we'll show a equals to b. Now, how do I do that? By definition, for every epsilon positive, you choose that epsilon, there exists capital N such that every time n is greater than that capital N, we get this situation. Now, do you understand this one? For every epsilon positive, there is a capital N such that for any term after that capital N term, the distance of the sequence from the claim limit A is less than epsilon. Of course, when n is greater than capital N, it implies n plus 1 also greater than n, right? In fact, that's strictly greater than n.
When you say a capital N, you mean it's just like the bigger number?
A very big number for which that. So let's go back a bit further. So when we say a sequence is convergent, it means, let's say the sequence look like this. Oh, see, I wonder what happened. I already want it to be in red color and it went back to black. So let's say the sequence convergent to, it doesn't have to be 0, a constant. Let's say this is a constant A. Okay, that's a constant A. Now, when we say the sequence is convergent to A, it means after certain term, if you choose any epsilon away from A, this is A plus E epsilon, this is A minus epsilon. Then there is a capital N. There is a capital N, let's call this the capital N, such that every term after that will fall into this strip. In other words, the distance from the limit is less than epsilon.
Okay.
Okay, now, so if the lowercase n term, let's say this term is already in that strip, then the next term must also be in that strip.
In the strip, okay.
Right?
Yeah, I remember this from your lecture video.
Now then, so we know that if it already passed that capital N, then the next term must also be in that capital N. Okay, now suppose by contradiction, it's also go to be, again, going back to that definition, that n plus 1 greater equals to another n we get this situation. So we will let capital N, a new n, which is the maximum of n1 and n2. So we can find another n which is the larger of these two, numbers, larger of those two numbers. My computer is screaming very loud. So sorry. So the larger of those two numbers. Then a sub then n plus 1 greater equals to that capital N, which is greater than n1 and n2, then both of these are satisfied. This is true, and this is also true. Is it right? Both of these things true for every epsilon. The key is at every epsilon. Any positive number you choose, I can always find that the difference is less than that positive number that you chose. Now, so what happened to the absolute of A minus B? Absolute of A minus B is absolute of A sub n plus 1 minus B plus A minus A sub n plus 1. Maybe I write it the other way around. Let me write it. See, I want to erase. So this is A minus A sub n plus 1 plus A sub n plus 1 minus B. Is it okay?
Yes.
Now, according to triangle inequality, the absolute of sum is less than equals to sum of absolute. Is it right? Because absolute of x plus y is less than equals to absolute of x plus absolute of y. So far so good?
Yes.
But then this is actually less than epsilon plus another less than epsilon. But epsilon is any positive number, right? So what is the number? What is the number that is greater equals to 0, yet at the same time always less than any positive number? Let me write it in words. What? So absolute of A minus B is positive or 0. Why? Because it's an absolute sign, right? So it must be positive or 0. Yet less than any positive number. What is the number that is positive or 0 and at the same time less than any positive number? Because your epsilon is any positive number you choose, right? You can choose any positive number. Now, whatever positive number you choose, this A minus B in absolute sign will always less than that. Then the only way is like A minus B is 0. Absolute of A minus B is 0.
Mm-hmm.
Therefore, A minus B is 0. Therefore, A equals to B. I do not emphasize proving in this class. That's why when it comes to proving, especially using epsilon and delta, I need to think from your point of view. I have to update my proof again. If I prove this in a class with a lot of proofing already, then I don't need to show it this way.
Yeah, this is a long proof.
Actually, this is short. Actually, this is short. When it comes to proof, this is actually short.
I guess it's because there's a lot of information in just like one line. I think that's why it feels like it's long.
So Robert has this question. So we had absolute of A minus EB equals to 2E. No, not equals to 2E. It's less than 2E. It's less than 2E. Okay, less than 2E. Right? Okay. So what is the number that is positive or zero yet less than any positive number? It must be zero. Okay. So you kind of like squeezed it from above using all positive number of your choice. So the key, one of the key, that's why this quantifier, do you call that I think, yeah, this is the quantifier. Okay, the quantifier that for every positive number. So this every positive number epsilon that you choose, okay, applies here. Applies to every positive number that we have. You chose earlier. Whatever positive number you choose, I will come up with n1, n2, and therefore an n such that every terms comes after this capital N will satisfy this condition, and that implies the difference of A and B, will be less than twice any positive number you choose. Okay. Now the thing is, if I did not write this part here, see, I want to change it to red, but it doesn't change to red. Now, suppose I don't write this thing, then that the thing here may be negative, right? What is the number less than every positive number? It's 0 or negative. So limit it below by 0, push that down to only 0. Okay, now of course in reality, if we have higher level way of proving, I don't even need to write this, but I don't even need to write this because it's already built in. It's absolute value, for God's sake, right? Okay, it's absolute value. So it's either positive or 0. So I don't even need to write that in. Okay, but just to emphasize that this guy is positive or 0, yet it is less than any positive number. Why is it less than any positive number? Well, because it's for every positive epsilon. You choose your epsilon. Okay, if it's not small enough, make it even smaller. But every time you make it smaller, I can always find that n. Every time you choose your epsilon, I can always find that n. Maybe different n from time to time. If you choose your epsilon 1/2, my n is 100. Maybe when your epsilon is 1/10, my n maybe is 1/1,000,000, right? But for every time you choose something, I will react with an n.
Okay.
Like that. This is quite heavy, I know, quite heavy, but good. Quite heavy.
All right. Thanks, Thomas. I'm gonna get off now because I have to feed my child.
Oh, okay.
All right.
Good to know. Okay.
All right. Thank you, Tom.
Okay. Okay, it's you, Robert. Do you have question? Other question? No more? Oh, okay. Well, okay, see you then. Thank you.